All right, let's take a look at topic number 26, logarithmic function. Okay, what is a log function? Very, very important. A lot of students not quite understanding what log function is. We know what an exponential function is. Very simple. Your variable x is on the exponents. Those are considered as an exponential function. What is considered as a logarithmic function is the inverse function. Remember, we talked about inverse function before. It's an inverse function of an exponential function. All right. So if I were to sketch an exponential function, normally look like this. Exponential function is a one-to-one function by using the horizontal line test. So if it's a one-to-one function, then we can actually find its inverse. Okay. So log function is nothing but an inverse function of your exponential function. And it's given by log. The way how we read this is log with the base a of x. Okay. Log with some sort of base, okay, of x. So on the graphing calculator, so we have, you might have a different graphing calculator in mind. If you actually take a look at the word log right beside number 7, okay, when I press the word log, it is automatically assumed the base is 10. Now, if your calculator displays log with a little box right here, then that box allow you to type in any base you want. But my calculator doesn't do that. Okay, my calculator does not allow me to type in any base that you want, that I want. So the older version of a graphing calculator, when you press the word log, it's always assumed the base is 10. All right. So right above the word log, you see something called 10 to the x power. The reason why is that 10 base is 10 because the button log is actually using base 10. So remember, log function is the inverse of exponential. So on the graphing calculator, all the opposite operations or the inverse of one the other is actually right next to each other. Okay. So that's the reason why x squared, the button x squared right above it is the square root because square and square root cancel each other out. They're considered as inverse to each other. And but then we find out, they have an inverse relation. They're not necessarily an inverse function to each other. Because remember, when we draw a parabola, it's actually not a one-to-one. So that's the reason why in the previous topic, there were homework problems regarding to only, we only have half a parabola. Okay. So as you can see, right below the word log, this thing called ln, L inverse ln is actually e to the x power. Okay. So far, if your calculator look like mine, every time you press the word log, it's assumed to be base 10. All right. So let's graph some of these. Okay, I'm gonna graph 10 to the x, then I'm gonna graph log of x. So you can see the two graphs that are inverse to each other. So to graph 10 to the x, I simply just say 10 raised into the x power, or I can use that second log. All right, for log of x, when I press the word log, it automatically give me a parenthesis. All right, what's inside the parenthesis is what the log is taking on. It's a log of x. Okay, log with the base 10 of x. So the first one is an exponential function, and the other one is your log function. They are inverse to each other. I'm gonna just zoom in a little bit. 10 to the x and log of x. All right, they are inverse to each other. The ln that I mentioned is actually called the natural logarithm. Okay, so when we change the base, okay, normally log with any sort of base a of x. If I change this base to a base e, which is actually log with the base e of x, okay, when we change the base to an e, then we actually get what we so called the natural log. Remember the number e we mentioned in the previous topic. It's about 2.7 something. It's actually, the e is actually used as a base. Okay, we use e as a base in this class. So when I change log from any number, 10, 2, 3, whatever, to a base e, we actually end up with what we so called the natural log. Okay, ln is denoted as natural log. All right. So on the homework at the beginning of the semester, when you do the syllabus quiz, I actually demonstrated how you can actually find natural log and log. All right, on the on the homework when you actually go to the graphic equation, I actually show you where those were at. All right. So let's graph it. Okay, let's graph and see what the difference is. Okay, I'm gonna graph e to the x, which is an exponential function. Then I'm gonna graph a natural log of x. So for e, you gotta be very careful. Don't use the alphabetical e. The base e, okay, the easiest one to use is actually right above natural log. So you can say, I'm gonna go to number one, natural log. I mean second e to the x, right? The second per second natural log. And on the exponent, inside the parenthesis, you just type in x. So that's e raised to the x power. All right, the next one, I'm gonna say natural log. And inside the parenthesis, I just type in x. All right, the first function is natural log. I mean, it's e to the x. Then the natural log is inverse. All right. Look very similar to 10 to the x power and log of x. Okay, so what's a log function? It simply is simply an inverse function of an exponential. What is a natural log? A natural log function is simply changing the base from other number to a base e. Then you actually end up with the natural log function. All right. Evaluate the following expression, run to 4 decimal places. Okay, so here I'm just want you to practice using your calculator a little bit. So log, if you don't see a base right next to the log, that means it's assumed to be base 10. So this is log of 100, which is 2. Okay, and I will actually show you how you can actually find that answer too. Natural log of 2. This is going to be an irrational answer. Natural log of 2. All right, 0.6931. Okay, it's an irrational number. You can never convert this type of answer into a fraction. So what happens if we need to graph? What happens if we need to graph a log function with bases other than 10? Well, there's actually a formula called change of logarithmic basis. For any log bases a and b, okay, for any log bases a and b, and any positive number m. By the way, you cannot take a log of a negative number. It does not exist. It's not a real answer. You can only take log or natural log of a positive number. Okay. If you take a natural log of -2, it's going to say not a real answer again. So here, what are base, base B can be any type of basis. So the A right here can be 10. The base A can be 10, or it can be base E. All right. So if you have a log with a base B of m, it can actually convert it into log with the base A of m divided by log with the base A of B. So let me show you right here. In order for my calculator to grab this function, since I don't have a syntax where I can type in a base 5, I need to convert this first term, the log term, okay, into something I can actually key it in. So log of base b of m. So the 5 is like my b. The x plus 4 is like my m. So once I convert this into, once I convert this, once I change this logarithm base, then I would say it's a log of a of m, log with a base a. A can be 10 or e. So I'm gonna use 10 first. So that would be log with the base 10 of m, which is x plus 4, over log with the base 10, A is 10 of B. B is 5. Okay. So sometimes you're gonna see me if it's only if I'm taking a log of one term, I don't put it in the parenthesis. If I take a log of two terms, I normally put them in the parenthesis. But the correct way is always put a parenthesis when you take a log or something. Okay, so if I forgot to write one, it's not a big deal. But make sure you remember if I'm taking a log of multiple terms, multiple terms will be in the parenthesis. All right, still minus one. Now the base can also be e, right? So I can also rewrite this first term as a natural log, right? Log with the base e is the same as natural log. So I can also write it as natural log of x plus 4 over natural log, right? Log with the base e of 5. Check this out. This is where it's crazy. All right. The numerator is technically only one term, but since I have a minus one and on the back side, I need to start a open parenthesis because my first term is in fraction. So I got to start with a parenthesis. And I'm going to say log of x plus 4. I'm going to close the parenthesis for the x plus 4 divided by log of 5. All right, I'm going to close the parenthesis for the log of 5. Then I'm going to close the parenthesis for my entire first fraction term, minus 1. I'm also going to type in the other one, natural log. All right. So again, this is two terms. So I'm going to open the parenthesis first. Natural log of x plus 4 divided by natural log of 5. Close parenthesis for the natural log of 5. Close parenthesis for the entire first term. Then minus 1. And this is what it looked like. All right. How many graphs do you see? I literally, if I go back to standard window, this is all you see. I just type in two functions into the calculator. Where are my the other graph? Where is my the other graph? It should be two graph. Why? Where's the other graph at? So what is crazy is these two are exactly the same graph. They are actually exactly the same answer. When you graph both of these functions using log with the base 10 or use a base e, you actually produce exactly the same graph. All right. Take a wild guess. Just by looking at your function, take a wild guess. What should Where should the domain begin? This thing is going to the right. So I know it's gonna go to infinity. But by looking at the function, looking at the picture, where do you think this function begin at? Based on what I told you so far. -4. You see, you cannot take a log of a negative number, right? It turns out we cannot take a log of 0. It's also going to be an error. So when x equal to -3, my function does exist. Okay. But when my x is -4, which is going to be give me a log of 0 or natural log of 0, then the y value becomes error. They don't exist. So the -1 we know is kind of telling us to, the entire function is shifted down one, your vertical shift. So this +4 in here also tell you that the natural log function or the log function has to shift it to the left 4 places. But it cannot equal to 4. So my domain is technically starting at -4 using parentheses because I can never, because the function is not defined at -4. But I can use -4 as a reference, right? So using parentheses, -4 to infinity will be my domain. Okay, I just want to point that out a little bit. All right, let's do some arithmetic work. So here are some of the very, very basic, okay, basic properties for natural log. We will talk more properties in a different topic. So right here is saying a log with some sort of base of 1 is always equal to 0. Okay, so if you take a log or a natural log of 1, it's always 0. You cannot take a natural log of a 0. Or, and you cannot take a log or natural log of a negative number. All right. Number 2, log with some sort of base of the same base will always equal to 1. So for example, if I take a log with a base 10 of 10, right? If I go to my calculator right now, when I press log, it's automatically base 10, right? So if I take a log with a base 10 of 10, my answer is always equal to 1. So in a way, it's almost like saying these two kind of cancel each other out. So you become 1. Same thing with natural log and E. Natural log and E are inverse to each other. So they kind of cancel each other out. So you end up with 1. You don't end up with 0, you end up with 1 when you cancel things out. Just like fractions, right? Just like when we cancel out top and bottom. If when everything cancels out in a fraction, it becomes 1 over 1, which is 1. All right, same thing here. If you have a log with some sort of base b of itself to the x power, well, the log with the base b of itself of the same base kind of cancel each other out, just like here, become 1. But so the only thing left is the exponents. That's why the answer is x. Same thing with natural log and e to the x power. Natural log and e, they kind of cancel each other out. So only thing left with is whatever that exponent is. Okay. And vice versa. If I put the base, if I put the logarithm on the exponent, when the bases are the same, they could always kind of cancel each other out. All right. So only thing you're left with is whatever that x is. Perfect example, if I have a natural log of e to the third power, the answer will automatically be 3 because natural log and e kind of cancel each other out. Natural log of e to the third power would just be 3. All right. So why is that the case? Why these answers become the way they are? Well, what's easier to comprehend is looking at these logarithm problems from the exponential perspective. Okay. So we can actually convert all the logarithm expression into an exponential expression or equations. So if I have a log with a base a of x, if I have any type of log with the base a of x, okay, if this base a is not 10, then I cannot put it in my calculator. So what we do is we set this expression into equal to another variable. All right, to convert into an exponential expression or equation, all you do is bring the base to the other side of the equal sign and put it in the bottom. Remember, a is a base, right? And you bump this y, whatever it is on the other side, to the exponent. Then you actually end up with an exponential expression. So if you take a look at this example, log with the base 3 of 81, log with the base 3 of 81. Set the logarithmic expression equal to y. So that means I'm going to take this entire log with the base 3 of 81, set it equal to another variable, just call it y. Number 2, convert logarithmic equation to an exponential equation. So all you have to do is bring the base to the other side of the equal sign and bump the y to an exponent. So this 81 is still going to be on the left side. The base 3 come to the right, bump the y to the exponent. So now we're actually looking at the logarithm as an exponential perspective. Remember, they are inverse to each other. Okay. So now we're actually trying to solve an exponential equation, basically. So number 3 here says convert the two bases into to 3. So 81, well, we know 3 squared is 9, right? So 3 to the 4th power got to be 81. So 81 is 3 to the 4th power, which is equal to 3 to the y. So once the base are the same, base are equal, we can set the exponent equal to each other. Therefore, y equal to 3. So what that means is, if I go back up here, log with the base 3 of 81 is actually equal to 4. So if your calculator allow you to type in a base 3 right here and you type in 81, you get a 4 and you're like, okay, it's 4. And the reason why it's 4 because we have to look at this logarithm expression in terms of what? In terms of an exponential. Okay, in terms of an exponential. So I'm gonna write this here on the side for you. Okay, let's see if it makes sense. You now know log with the base 3 of 81. That 81 is the same as what? As 3 to the 4th power, right? So if we follow the reason why the log with the base 3 of itself, the same base, cancel each other out, is because if you actually set this expression equal to a y, move this over, move the base over, you actually end up with 3 to the 4 equal to 3 to the y power. So y equal to 4. That's the reason why once the base are the same, once the bases are the same and what you're of, when the base and what you're of are the same, they kind of cancel each other out. Because the whole idea here is trying to what? Make the base the same once you convert them into exponential. So you can quickly see, okay, now I see why this answer equal to 4. Otherwise, none of these answers seems logical. Okay. All right, let's try another one. Okay, I'm gonna set this entire logarithm expression equal to y. This is actually a fifth root of 64. Convert the logarithmic equation into an exponential. So all I gotta do is bring the base to the other side and bump the y to an exponent. So what the log of is should still be on the left side. All right, I need to convert the two bases into a 4. 64 itself is 4 to the 3rd power. All right. But this 64 has a fifth root, has a radical on the outside of it. So if I convert the fifth root, the radical into a fraction exponent, if I convert into a fraction exponent, then remember denominator determines the roots. The numerator tell you that the base is raised into that power in the inside. So technically, fifth root of 64 is the same as 4 to the 3 over 5 power. Okay. So some of these things we learned before how to convert radical into a fraction exponent or rational exponents. Okay, come in handy now. So now when the base are the same, base are equal, I set the exponent equal to each other. Therefore, y is equal to 3/5. So if you actually think about, okay, this entire expression is equal to 3/5. This answer is not logical by looking at your problem. The reason why it doesn't seem logical is because we are actually trying to look at this logarithm in terms of an exponential perspective. Then that actually made more sense. Okay, don't look at logarithm expression as a logarithm expression and then trying to make sense out of the answers. This answer is really looking at from an exponential perspective. All right, let's try another one. Okay, this time is log with the base 2 or 1/16. So same thing, set it equal to y. Number 2, convert the base. I'm gonna move the base to the other side and bump the y to the numerator. Okay, so what the log base 2 of should still be on the left side. Now it's equal to 2 to the y power. All right, I want to convert the two bases into a base 2. So 16, 1/16. 16 is 2 to the 4th power. I want to convert into a base 2. So that means this base needs to move over to the other side of the fraction. So when I move the base to the other side, okay, now since my exponent was positive, now when I move it back to the top, it will be negative. So this is actually 2 to the -4 power equal to 2 to the y power. Therefore, y is actually equal to -4. Okay, I hope this kind of makes sense. Okay, we really got to stop thinking about looking at the logarithm expression and then trying to make sense all of the answers. The answers only make sense if you actually think about them as an exponential perspective. All right, let's try another one. Okay, this is base 1/4 of 16. I'm going to set it equal to another variable. Okay, move the base to the other side. So that should be 16 equal to 1/4 to the y power. Okay, I can put a parenthesis here if I want to, but you know what I mean. All right, I want to convert the two bases into a 4. All right, I know 16 is 4 squared, no problem. 1/4 to become base 4, I just got to flip this to the other side. 1/4, flip a base to the other side. So that becomes 4 to the -1 power, because this 4 was to the positive 1 power down in denominator. Okay. Now remember, on the very outside, I had a y power. So now, if I apply power rule here, that should be 4 to the -y power. All right. So if I solve for y, this is now going to be -y equal to 2. Therefore, y is equal to -2. Y is equal to -2. Okay. All right. Log with the base 64 of 8. I'm going to set it equal to 8. Excuse me. No. Log with base 64 of 8 set equal to y. Bring the base over. So that should be 8 equal to 64 to the y power. This time I want you to convert into a base 2. Base 4, excuse me, base 4. No, I cannot convert base 4. 8 cannot convert into base 4. Sorry about that. It's base 8. Base 8, okay? If I convert into a base 8, then this 64 is now 8 squared. Well, since the 64 had a y power on the outside, according to the power rule, if I multiply the exponent, that should be 8 to the 2y power. So this is 8 to the first power equal to 8 to the 2y power. So 2y is equal to 1. Set the exponent equal to each other. Y is equal to 1/2. So that's 1/2. All right. So what happens if you cannot make the base the same? What happens if you cannot make the base the same? There is no way. If you just look at this log with a base 5 or 8, there's no way I can make base 5 into a base 8. So when you cannot make the base the same, you had to use that formula I showed you earlier, changing the logarithmic basis. Earlier, I used that formula to graph, but I can also use that formula to evaluate expressions. All right. So I normally prefer, okay, if I don't see an E anywhere, I if I don't see an E anywhere, I just use, base 10 for logarithm. Oh, my pen is out. Hang on 1 second. Let me see what's wrong with my pen. It's all right. So log, ooh, this is gonna be hard to write. I just changed the battery. I don't know why the sensor is not working. There it goes. All right, log with the base b of m is equal to log base a of m over log with the base a of b. All right, so I'm gonna leave the 6 out for a moment, okay? So far I got log with the base 5 of 8. So basically the b is 5, the m is 8. The base a in my formula can be e or 10. But if I don't see E anywhere, I don't think about using base E. So I'm gonna use regular base 10, okay? So log with the base 10 of M, log with the base 10 of M, okay? So when I go to my calculator in a minute, when I press log, it's all right, automatic base 10 over log with the base 10 of B, B is 5. All right, 6 times in front of it. So I'm gonna put 6 times in front of it. So 6 times something is 6 over 1. So that actually I can actually put the 6 as a numerator too when I type it in. So this is 6 times log of 8. This is only one term divided by one term log of 5. Okay, I don't need extra parentheses because everything is only one term. 4 decimal place, 7.7522. There you go. When the base cannot be the same, if you cannot make the base the same, then you have to use the change logarithm basis formula to help you evaluate the answers. All right, let's look at some homework questions. What is the inverse function of an exponential? A logarithmic functions. Is an inverse function of an exponential. When we change the base of log from a regular base a to an e, we actually get natural log. Once you get natural logarithm. Question number 3. All right, let's do exactly the same thing I just showed you earlier. Okay, so set the expression equal to a y, and then move number 2, move the base to the other side and bump the y to an exponent. All right, convert the radical. So number 3, I want you to convert this radical into a rational exponent. Okay, fourth root of 27. convert the radical fourth root into a fraction exponent. Keep the 27, okay? Keep the 27 in the parentheses. Then convert the two bases into a base 3. All right. It's when I say 3 because earlier I was taking a log with a base 3. So I want you to convert the 27 to a base 3. But since you already had a rational exponent from 3, from number 3, then I want you to go ahead and apply the power rule like I showed you earlier. Okay, so you should be 3 to some sort of exponents here. All right, and then solve for the y. So just quickly showing you what our logarithmic function is, okay, and how we actually change logarithm into an exponential and actually simplify expression from that perspective. All right.